This lecture, we are going to look at polynomial functions and maybe some models. The models are pretty, I think, straightforward, so you'll just see it's, you know, different things can be modeled with polynomials. But this chapter really is getting into how we can talk about graphing polynomial functions, and we'll start talking about graphing rational functions as well. So before we get too crazy, let's put down a definition, or maybe we're already there, who knows. So definition, what is a polynomial? I imagine if I asked you to, give me an example of a polynomial, you could easily do that. But how do mathematicians define polynomials in the most general way? So a polynomial function, let's call this P, polynomial, we're pretty creative here, is given by the following. And this is just one way to describe all polynomial functions. So it's a function of x. Usually it doesn't have to be x though, right? Maybe our polynomial is describing the height of a ball thrown up and coming back down as a function of time. So it could be t as well. But we have a sub n, x to the n. So that a sub n is going to just represent the coefficient for the nth degree term. Okay, and then we'll go down from there. A sub n minus 1, x to the n minus 1. Subscript notation is really useful because we don't know how many terms we have, right? So if I had used a, b, c, d, I would be limited by 26 terms because of the alphabet, which heaven forbid we have one bigger than that. But that subscript notation, again, is pretty nice because it allows us, it doesn't put a restriction on the number of terms I have. And these polynomials, we should not have a restriction for that. So this is what we mean by a polynomial function. This p of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus, thank goodness for the dot, dot, dots, a sub 2x squared, a sub 1x, and a sub 0. Now, we don't have to have all of these coefficients either, but let's just say let's define kind of what these guys are. Whoa, what just happened? I seem to do that. A sub 0, a sub 1, dot, 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 up to a sub n are real numbers. So the quick way of writing that are elements of the real numbers. I don't know if you've seen that notation before, but that just means elements of. The capital or the bold R means the real numbers, and we call them coefficients, called coefficients. So I need to have real numbered coefficients. I don't have to always have that, but for in this class, we're going to have real numbered coefficients called coefficients, and the exponents must be, so this is the important part about something being classified as a polynomial, is that the exponents are whole numbers. So remember what whole numbers are. Whole numbers are 0, 1, 2, 3, 4. It's all of your natural counting numbers and then with 0 in there. So that's what we mean by a polynomial. I'm sure that you have heard that before. If we have a polynomial, just a little bit of terminology here. If this is my polynomial and it's written in descending order, then we say that the leading term, okay, so let's assume this is written in descending order, then the leading term is the term, including the coefficient, with the largest exponent, okay? The leading coefficient is just the coefficient of that term. Oh, sorry about that. So the leading coefficient in this case would just be a sub n. And then finally, what's the degree of this polynomial? The degree of the polynomial, which I'm sure you heard before, the degree of the polynomial is just the largest exponent, okay? So that's what we mean. Again, this is assuming that this polynomial is written in descending order, where descending order means you have the term with the largest exponent first. So that's just some kind of verbiage about that, and we can kind of classify polynomials into different things. So let's look at a couple examples where we kind of classify them. So if I have, they do kind of a nice little table, so I'm going to copy that. And I'm going to copy this from your, so degree, let's look at leading term, and let's find the leading coefficient of each of these. So we're kind of coefficient. I'm going to abbreviate that. So if I'm given a polynomial, I'm going to give you an example. Actually, what I mean by polynomials will describe what that is called. So a constant polynomial, could we have a constant polynomial? Of course you can, right? So look at here. This didn't say that I have to have an x value. I could have a constant polynomial. That's just going to be of degree 0, we're going to see. So if I have a constant polynomial, like f of x, I don't know, pick your favorite number, right, equals 42. If I have f of x equals 42, that degree is 0. Degree is basically the largest exponent of your x values. Technically, if we have 42, we have an x to the 0 here because x raised, or anything raised to the 0 is 1. What's my leading term? Well, then my leading term is going to be 42. And what's my leading coefficient? Also 42. Okay, so that's what we mean by a constant function. So what if, let's go up here, if we do have an x value, so let's say f of x, doesn't really matter what we have, f of x equals 1 minus 2/3 x, right? And I don't have that in descending order, but if I did, what would go first? That negative 2/3 x. So what's the degree of this polynomial? It's 1, because this is x to the first power. The leading term is the negative 2/3 x. If I wrote it in descending order, I would have negative 2/3 x plus 1. And then what's my leading coefficient? It would just be that negative 2/3. I think that's pretty simple. That's what a linear is, a degree 1 polynomial. A degree 2 polynomial, we know what those are. We've already been working with them. Those are what we call quadratics, right? So something like f of x equals 1/10 x squared minus x plus 4. Okay. And I'm running out of room here. I'm gonna give myself a little line here so I don't go through that. Oh, sorry about that, guys. Look at those lines. I'm doing good. I'm doing well. I'm a math person. I don't need to know how to talk good. Okay, so what's the degree? It's 2. That's how we know it's a quadratic. What's the leading term? It would be 1/10 x squared. We know that because that's the first one. And the leading coefficient is 1/10. Okay. How about a third degree polynomial we call a cubic? So f of x, I could have, a negative x cubed plus x minus 3. Do I have to have every single term? Like for instance here, I don't have a squared term, right? No, I don't have to have that. For it to be a cubic, I just need to have a cubed term, and that's it. X cubed by itself with no squared, no linear, anything, that is still a cubic, right? So my degree is 3 for a cubic. My leading term in this case is a negative x cubed. And what is my leading coefficient? It'd be a negative 1. And then finally, we'll just do a quartic. Now, is there a limit on the degree? Nope, there is not. But when we start kind of giving them names, I think there's a limit on the names. A quartic, I think, is obviously, it is not, I think. I know. Is the 4th degree. So, I could have, 0.5 x to the 4th minus 1. I'm not going to put the other terms just because I don't have room. This is degree 4. What is the leading term? 0.5 x to the 4th. And what's the leading coefficient? Just a half. So quartic, I don't remember what I think a 5th degree polynomial is like a quintic. If you're watching this and you're yelling at me right now, but that's all right. I'm all right. I understand. So I hope that makes sense. So there's a lot of things that we can know about these polynomials. Okay, so if for example, what we're going to kind of talk about is like what do I know about the graphs of these polynomial functions? How are they the same? How are they different, right? By the way, something that is not a polynomial function would be something like 4x to the 1/3 minus 2x. Why isn't this a polynomial function? Because it doesn't have a whole number coefficient. Or likewise, if I have like 4 to the negative 2 plus 2, that's not a polynomial because I have a negative exponent. So polynomials must have whole number exponents. So what I want to look at now is we want to see if we can see some things that are similar. Oh, yeah. I know. In terms of their graphs. And if I look at this function, what can I kind of tell about it? So let's first look at maybe just a simple quadratic function. So I think the quadratic function, oh shoot, now I don't remember, that I used is x squared minus 4x minus 12. So I want to actually show you this. So I'm just going to use Desmos. This lecture, it's not brought to you by Desmos, but we're going to use it. So I have this x squared minus 4x minus 12. We'll look at these guys later and kind of see what's happening. But if I put this in, we know what this is going to look like. We've dealt with quadratics before. Right, we've dealt with, we know what they look like, they're parabolas. I can see a couple things here. If you notice here, I have a 0 at 6. I also have a 0 at -2. I can talk about my y-intercepts, right, being 6, 0, and -2, 0. I can also talk about, sorry, did I say y? I meant x. I can talk about an x-intercept. My x-intercept is 0, -12. And then we've talked about, you know, having maximums and minimums. Has a max or a minimum, which is -16, as you can see by my cursor there. No maximum because it goes on forever. Domain, all real numbers. And then if you look at your range, you know, what's my range? -16 to infinity. So there are a lot of things that I can look at and understand about polynomials just by kind of looking at their graphs. If you think about a polynomial, what is the domain of a polynomial? Everything, right? Everyone's invited to the party. I don't have any fractions or anything like that. Let's look at this function right here at my cubic function. Well, before we do that, actually, let's go back and see. So if I look at this x squared minus 4x equals 12, I can determine a lot of things about this, the graph of this. I can determine that stuff algebraically as well. For instance, to find the zeros of this function, right, I can take this guy and set it equal to 0, obviously. Going to factor x minus 6, x plus 2. That's going to equal 0. So what does that imply? The zeros of my function then are 6 and -2. So then likewise, my x-intercept then, right, if I let y be 0, I'm going to have the same thing except my x-intercept should be written as a point. So my x-intercept, we're going to go through -2, 0. And then if I wanted to find my y-intercept, if you notice, I would just let my x terms be 0, and I would be left with -12. So I have 0, -12. This guy also is pretty obvious that my domain, right, just looking at it algebraically, is -infinity to infinity. Now I could talk about my range. Maybe I could switch my x and y's and mess with that a little bit. But my range, I would want to look at, whoops, I want to look at that graph, right? And we see that my range, then I'm starting down here at a -16, and then it goes up. And so my range would be -16 to infinity. So pretty interesting stuff. Let's switch this around a little bit and look at maybe a different function. So that's an idea of what kind of a quadratic would do. Let's look at maybe a cubic. Oh my goodness, is that annoying you? It's annoying me as well. So y equals, and I don't remember what cube. So let's look at this one then. So y equals x cubed minus 2x squared minus 3x, and see if we can kind of decide what might happen to this graph. So that's x cubed minus 2x squared minus 3x. So this is a cubic. Its leading term is x cubed. Its leading coefficient is 1, has degree 3. So if I wanted to find the zeros of this function, I'm going to take this polynomial and set it equal to 0, hence the name zeros, right? I'm going to take an x out, and I get x squared minus 2x minus 3 equals 0. And then, you know, I can set x equal to 0. Well, this one's pretty easy. Let's just keep factoring in here. So this is x times x minus 3 times x plus 1 equals 0. So what are my zeros? 0, 3, and -1. So likewise, that's what I have for my x-intercepts, right? My x-intercepts would be 0, 0, 3, 0. So we go through the origin. -1, 0. My domain, definitely all real numbers. Everyone's invited to the party. Polynomials are great. They're really social. They let any x values come to the party. And now let's see our range. So you might have an idea of the range here if you know what x cubed looks like. If you remember that when we talked about transformations, right? X cubed looks like this. And because this guy has a cubic and has the highest degree of a cube, we're going to see that the graph of this is going to be very similar to the graph of x cubed. It's just going to be a little funkier. So do you see this is pretty nice, nice graph. If you notice, well, we're having to think a bit here, but if we notice here, I definitely go through 3, 0, right? There's 1, 0. Here's another 0, 0, 0. And then there's my other 0, which is negative 1, 0, which those are the ones we have found. Domain is infinity to infinity. Oh, we didn't talk about our y-intercept. We'll talk about that. Well, if you look at this, you can see it's 0, 0. And then if you look at your range, clearly we can get any value we want. So my range is going to be minus infinity to infinity. So let's go ahead and put that. And how do we know our y-intercept is 0, 0? Well, if you put in 0 for x, right, clearly if I put in 0 for x here, I get the point, 0, 0. And I like this graph because you can kind of see that it is going to kind of remind you, right, a little bit about what x cubed would look like normally without having done that stuff to it. So it kind of messes with that x cubed a little bit. All right, let's look really quick at a quartic and then we'll talk about something called end behavior. Man, I'm sorry I keep doing that. And the quartic I want to look at is going to be x to the 4th minus 4x squared. So let's look at that. X to the 4th, so f of x or y, I don't know, I use them interchangeably. X to the 4th minus 4x squared. So let's look at how do we find the zeros of this. Zeros of this, again, I'm going to set this guy equal to 0. I'm going to factor out an x squared. I would get x squared minus 4 equals 0. And now I'm going to factor again. I like to factor these so that I don't forget to bring in the plus or minus, because sometimes I forget to do stuff. So what are my zeros then? I'm going to get 0, right, with that x squared. We're going to talk about that as our multiplicity later on. 2 and negative 2. So my x-intercepts then, it's going to go through the origin, 0, 0, 2, 0, and negative 2, 0. Y-intercept, if we let x be 0, clearly that guy's just going to 0. So it's going to go through the origin. Excuse me. Domain is going to be minus infinity to infinity. And then for range, you know, the thing I don't know exactly what's happening with this, but I know that I have that x to the 4th as my leading term, and I know when I take something to the 4th, it's always positive. So I feel like, well, I kind of know, but I feel like my range is probably going to be restricted somehow. I don't think it's going to be minus infinity to infinity, but let's see. Oh yeah, ooh, look at that purple. Isn't that pretty? All right, so let's look at what we have. These are the zeros that we thought of. We have the 2, 0, we have 0, 0, and we have negative 2, 0. Okay, so that's pretty cool. Does go through the y-intercept like we thought. This guy actually does have a minimum value, which we talked about that kind of with the quadratic. Did I talk about that with the quadratic? Well, I'm going to talk about it now. So if you look at the minimum, this function actually has a minimum. And what is that minimum? That minimum is going to be negative 4. Look at where those negative 4s occur. That's also going to be how we describe our range then. What was the smallest y could be? The smallest it could be was negative 4, and then it went up from there. And this, we should have talked about that on the quadratic, but this function also has a minimum. And what is that minimum? That minimum is negative 4. Okay, so that's what we're talking about when we're talking about polynomials. Some things about polynomial functions is that polynomials are what we say continuous throughout the whole graph. So what do I mean by continuous? I mean there are no breaks. When you get to calculus someday, you will define continuity in terms of limits. But really at this level, what does it mean to be continuous? It means I can graph the function. You've probably heard this before without like lifting your pencil or your pen. Okay, so no breaks in the graph. So for example, some of those piecewise functions we did, where they maybe went like this, right? Maybe we had a piecewise function that did this. This is a function that's clearly not continuous because I have breaks in the graph. All of these polynomial functions like this one, right, these are all going to be continuous because I can kind of graph it without lifting my pencil. That's the idea of a function like that. All right. So the next thing that we kind of want to talk about is something called the leading term test. And if we look at some of these graphs, so let's look at some of these graphs and get an idea of what might happen with these leading terms. So if you notice, x to the fourth, okay, leading term tests are basically going to ask us what the end behavior of the function is going to do. So if I look at a graph like this, like x to the fourth, do you notice how it goes, the end behavior of this function, and sorry, it's giving me that circle. It goes up on both sides. And even if I did some stuff to this function, so let's say I, added 5x to this. Okay, so I've kind of messed with this function a little bit and it's made it look a little weird. Oh, that's really cool. But if you notice, I'm still going to get the same end behavior where it goes up and it comes up here. This is going to be the same for x squared. If I look at x squared, okay, if I look at x squared, I could do other stuff to this. Like, I don't know, let's get rid of the 4x. Am I still going to get the same end behavior with x squared, with that leading term being x squared? I am. Now, what if I put in, 0.5 x squared? Do I still get that same method of it going up? I do. And what if this leading term, instead of an x squared, what if this was like x to the 6th? Oh, look, I get the same thing. What if it was x to the 10th? Oh, how about that? How about x to the 106th? I really, really like that. Wow, that's, the computer can't quite handle that. But what does this mean? So if you look at these two functions, if you look at this one and this one, the exponent on those are positive. So that's what's going to help us determine what is going to happen when I have a different type of degree. Okay, so if I have a positive degree and the leading coefficient of that polynomial is positive, did I say positive degree? Excuse me, even degree. And the leading coefficient is positive. Okay, then I'm going to get an end behavior like the ones I've been seeing where both ends go up. Could the both ends go down? Yeah, they sure could. The way that those both ends would go down, and we know this from when we looked at these graphs before. Let me get this so that you can see it. Let's say plus 3. Okay, if I have like x to the 10th plus 3, if you notice what happens to the end behavior, I'm still going in the same direction on both ends, but they're just going down now. I could get that if I look at my x to the 4th. Oh, I did not mean to do that. Darn it. But if I had my x to the 4th, right, and I just wanted to, what did I have there? I think I had minus x squared, yeah? Okay, so x to the 4th minus x squared, if we graphed that guy, look, again, I have kind of that same behavior, right? That same behavior where, and if we put like a 4 in there, no, that's not going to work because that gives me an unreal solution. But what if I put plus 4? Okay, so look at, I still have that same end behavior stuff, kind of crazy stuff's happening in the middle here, but I still have that same end behavior where both ends are going down. So what do we know from this? An even exponent is going to cause the graph to either both go up or both go down as I think of x getting really, really big. As x gets big, what's happening to my y values? The other thing, and you probably guessed this, is what happens if I have something that isn't even. So what happens here, if you think about this, when I have this odd function, or odd degree, excuse me. Remember when you take a negative and you take it to an odd degree, you get a negative out. So for a graph like this, I can have positive y values, I can have negative y values, and they can go down forever, they can go up forever. So something like this, like x cubed, it's going to be an increasing function for when we're talking about the end behaviors. Increasing. I know it decreases right here, but if I'm just looking at the end behaviors, then I have them opposite. Okay, this would be true also. Okay, if this was, let's grab a different number. How about not 3? How about 5? Okay, so let's graph x to the fifth plus, and let's make this a little bit smaller, maybe plus just x, okay? So x to the fifth plus x. If I look at this, let's go in on this a little bit. Again, if you notice the end behavior on this, this side down here, whoops, sorry about that. This end down here, right, it's going down, but this end is going up. So what we say is it has opposite end behaviors, okay? And that's going to be true anytime we have an odd exponent. And how could I get it to switch? What if I put a negative? Look at what that does. The negative just makes it go, instead of increasing to all the way, it goes decreasing. Might go increasing here, but that's okay, and then decreasing. Same thing here. What would a negative do in front of that term? Right now, if you remembered before, okay, before I had this graph that was kind of increasing, my end behavior was increasing. Now if I put a negative in front, what is my end behavior doing? It's going down like that. And we can change coefficients to see if we can make it do more fun things. Yeah, that's not helping. Sometimes I just sit here and mess with it. Oh yeah, that was fun. And I waste a lot of time just messing with these because I think they look cool. All right, let's write this all down. I think I was rambling a little bit, which you're probably used to by now. But let's write down what we mean by end behavior. This is called the leading term test. Okay, and this leading term is going to tell us the end behavior of this function. Okay, so when we have an even degree, so even degree, wow, I keep doing that. Oh, I did not probably erase her there. Even degree. Here's what's going to happen if I have an even degree. So if I have an even degree and it's like ax to the n, and this is my leading term, right? An even degree leading term. So that means n is even. If a is positive, think about a quadratic, right? Then I'm going to have the same, we kind of saw that before, I'm going to have the same behavior on that leading term at the ends. Okay, so sometimes you'll see graphs do like this, where it's just saying inside it may do something funny, like I may have a graph that goes like that, right? But do you see how the end behavior is similar to what's happening here? That's what's going to happen if my leading coefficient is positive. If my leading coefficient is negative, all that does is it can take all the y values and switches them around. So we're going to have a graph that kind of looks like this. So they'll just give you a little blank in here in between, just so you realize that it could do other stuff. Again, I could have a graph that goes like this, right? But, or I could have a graph that goes like this. But do you notice my end behavior is the same? Okay, so that's what we're going to have if we have an even degreed polynomial. Even degreed polynomial. And then you look at your leading coefficient to determine if it's going to open up or down. So odd degree, it's just they're going to be the opposite. You guys should do dances with these. I'm sure that if you look, so where n is odd, and this is my leading term, if this is positive, the way I remember this one is I think of x cubed. I know that x cubed does something like this, right? But again, stuff could happen in between here. So x cubed does something like this. So I just kind of graph x cubed in my mind. And then I think about, well, what if that a is negative? I know that would give me a reflection. So I know it would go like this if my coefficient was negative. Okay. Again, stuff could happen in between. So maybe I would have something like that. Oh, those are beautiful. Or maybe I would have something like this. That's not even a function. Just pretend. So that's what we mean by the end behavior. So let's look at a couple examples of that. All right, let's clear that out. So describe, I don't know really how you describe that, but let's just describe the end behavior of each polynomial. And that's using this leading term test, okay? This is only for polynomials. All right, whoops. And decimals is a great way to, verify what you're doing. So let's look at f of x equals 3x to the fourth minus 2x cubed plus 1. So what you want to look at is you want to look at two things. So first off, what is the degree of this polynomial? It's 4 and it's even. So I know that I'm going to have the same end behaviors. Like if, in football when you do a touchdown, it's either going to be up being a touchdown or down being not a touchdown. I don't know what that means. So I'm going to look at it's an even degree, and then I notice my leading coefficient is positive. So the end behavior that this guy will have is it'll both be going up. That's exactly how I want you to describe it with one of those little things. You don't have to do the squigglies in between. I don't think my math lab has you do the squigglies in between, but that's the formal word for it too, squigglies. What about a negative 5x cubed minus x squared plus x minus 10? All right, so again, I'm going to look at the degree of the polynomial. I look at this degree and it's odd. That means it's going to be the opposite end behavior on each side. And then look at this as negative. So again, what I think about is I know x cubed looks like this, regular old x cubed. And so what that negative is going to do is it's just going to reflect it. So instead of increasing, I'm going to kind of be decreasing, except for I might have some stuff going on inside it, right? Might have some stuff going on inside. C, what if we add f of x equals 4 minus x to the 6th. Okay, 4 minus x to the 6th. If I look at this guy, what is my degree? It's even, so I know I'm going to have either a touchdown or not a touchdown. How do I know it's not a touchdown? If I bring my arms down, that is a negative coefficient, so that means I'm going to be opening down. So my end behavior is going to look like this. Okay, and you can graph all these and verify that. I mean, that might be what you do anyway, is just graph it and know. But sometimes it's nice, like even in calculus, if I'm given a function, oh, I know that this guy's opening up, right? And it's an even degree, so I know it's going to have a minimum. Or I know it's going to have a maximum, and then when I go through and maybe do the calculus with it, then you might see that. Or how about f of x equals x to the 7th minus 5x to the 6th plus 4x to the 4th plus x squared. Now, notice a lot of these exponents are even. However, what is my leading exponent, or what is the degree of my polynomial? It is odd, and the coefficient is positive. So I'm going to have, it's going to look like x cubed, except some crazy stuff could happen in the middle. Okay, I hope that all kind of makes sense. Okay, we are getting close to being done with this section. What I would like to talk about now really quick are the zeros and the multiplicity, and then I'm going to let you look at the models. They're not too hard to deal with, so I'll let you kind of do that. So let's look at a couple examples. We've already looked at a few examples of finding zeros, but I would like to do a few more. So one way that you can determine if a number is a zero of a function is you just plug it into the function, and if you get 0, I don't think I need to probably show you that. But what I want to look at is finding zeros and then maybe what they mean about the graph of the function and kind of what they tell us about the graph of the function. So we've already looked at the x squared, we already looked at, we already looked at f of x equals x squared, what did I have, minus 4x minus 12, and we saw that those zeros were 6 and negative 2. And again, what does that mean? If I put in 6 and if I put in negative 2, this function is 0. We also looked at f of x being x cubed minus 2x squared minus 3x, and we found that those zeros were 0, 3, and negative 1. And then we also looked at a function f of x equals x to the 4th minus 4x squared, and we found that our zeros here were 0, negative 2, and 2. Okay, so that's what we mean about the zeros of the function, and sometimes these can be tricky to find, sometimes they're not too bad. What if we had something, sometimes it just takes a couple algebra tricks. If we had something like this, x cubed minus 2x squared plus 9x plus 18. Remember, this is when we factor by grouping. Take out an x squared, you're left with x minus 2 Here, what can I take out of here? I can take out a 9. Oh, I messed up. Sorry. That's not, there we go. That's better. Minus 9. I'm going to take out a negative 9 so that when I take that out of the 18, I get minus 2. So this one's kind of cool because we get x squared minus 9 then. If I take that x minus 2 out, I just get x minus 2. And then x squared minus 9 is x minus 3 times x plus 3. You guys should know how to do this. X equals or minus 2. So what are the zeros in the case of this function here? 3, negative 3, and 2, right? And if we put a 0 or put that with a 0 after it, we can get our y-intercepts pretty easy. So that's kind of how we're going to find zeros. Sometimes, let's look at another example. Sometimes it's factored for you and life is easy. So like something like f of x, what if I had like f of x equals a negative x plus 1 cubed times x minus 2 times x plus 3, right? So look at the zeros here. This is already factored for us. What would make this term 0? Right, that term would be 0 if x was negative 1. This term would be 0 if x was 2. And this term would be 0 if x was negative 3. So pretty easy to see the zeros there. If you're looking at this, what would the degree of this be? I don't want you to FOIL it out. No one wants to FOIL that out. That would be gross. So just to look at this and kind of see what's happening, what would the degree of this polynomial be? If I cube this whole thing, the biggest term I'm going to have is an x cubed. Then that x cubed is going to be multiplied by an x somewhere along the line, which would give me an x to the 4th. And then that biggest term, x to the 4th, will be multiplied by another x somehow, which would be x to the 5th. So the degree of this polynomial actually is going to be 5. I have 3 x's here, 1 x here, 1 x from this factor. And when I multiply, right, I get, I add their exponents. So we're going to get something like that. This guy, I don't even know what the graph of this guy looks like, but we could graph it on Desmos and it would be fun, except I feel like I'm getting kind of far in my lecture here. So what are the, so really quick, let's talk about what these zeros have to do with the graph of the polynomial itself, okay? And we're going to talk about something that is called multiplicity, okay? So let's look at, I'm going to just write this down. And then I'm going to talk about what that multiplicity means, okay? And then we'll be done. Even and odd multiplicity. Okay. So even and odd multiplicity, let's just write this down. So what I'm basically looking at is what is happening with these factors that I have. So like, for example, this x plus 1 cubed. So this x, I'm going to say we have x minus c to the k, where k is greater than or equal to 1, which is kind of like duh. Let's say that that is a factor of p of x, and p of x is a polynomial. I'm not going to write that. We're just going to assume that, okay? And let's say that x minus c to the k minus 1 is not a factor. I'm sorry, I meant k plus 1. That... I actually had to pause there. I'm like, wait, that doesn't make sense. What that means is basically I've grabbed the most x minus c's I can. Like I have this x plus 1 to the 3rd. I don't have another x plus 1 to the 4th or something hanging out there. That's all that's saying. And here's what we got then. Here's if k is odd. So if k is odd, then what we say is that this factor right here has odd multiplicity. Then the graph, and I'm going to show you examples of this, crosses the x-axis at c comma 0. Okay, so it's going to cross through the x-axis at c comma 0. Here's the thing though, if k is even, what this does is it kind of comes down and it kisses the x-axis and then it goes back up. So it's almost like an end behavior thing. If I have a 0 that is the result of a factor that has an even exponent, we say it has even multiplicity, and if k is even, then the graph, how do we say it comes down and kind of kisses the x-axis? We say the graph is tangent to the x-axis at that 0. I'm going to show you a bunch of examples. okay, at c equals 0. Okay, so let's look at some examples. I'm going to put my computer up here so this is easier to do. And let's go back to this guy here. So let's get rid of that, and I want to do the one we just did. So I believe we had, yeah, we had a negative of x plus 1 cubed and x minus 2. So negative of x plus 1, right, cubed times x plus 2, was it? Oh, I already forgot. That's so sad. X minus 2 and x plus 3. Minus 2 and x plus 3. Okay, so this is what we mean by multiplicity. So if you look at the graph of this, this is great. Love this. If you notice, I have 3 zeros, and each of these zeros have what we say an odd multiplicity. When we look at this negative 1, this is, we call this a multiplicity of 3, and that 3, and where does that multiplicity come in? It comes from this 3 right there. That's what we mean by multiplicity. And if you notice with all of these zeros, do you see how, just like in our definition here, it crosses the graph crosses the x-axis, okay? So it crosses that x-axis, it comes through, it crosses right here at negative 3, crosses at negative 1, and it crosses at 3. Whereas when we had this graph before, x to the 4th minus 4x squared. Okay, wow, we're getting way too many graphs here. Look at the difference with this one. Okay, remember x to the 4th minus 4x squared. Do you remember we factored out? Let's take the factored form. We had x squared, right? And then we had x minus 2 and x plus 2. So this is the factored form of that graph. Look at 2 and negative 2. Their multiplicities are 1 because it's 1, the exponent on that factor that makes it 0 is 1. Do you see how the graph goes through that 0? And the graph goes through that 0 here. Whereas if you look at this factor right here, what x value makes that factor 0? 0. What is the multiplicity of that 0? It is 2. And do you see how the graph doesn't actually go across the x-axis there? It comes up, it kind of kisses the x-axis and goes away, or what we say is it's tangent to the x-axis. I could draw the x-axis would be a tangent line. I hope that makes sense. Let's look at a couple examples and then we will call this good. Okay, so for example, if I had something like f of x equals x minus 4 squared times x plus 2 cubed times x minus 1 times x. This is a little crazy, but let's look at the zeros we have and let's state the multiplicity. Excuse me. So let's state the zeros and let's state the multiplicity. This is what I mean by multiplicity. So the zeros, 4 is a 0. What is its multiplicity? Its multiplicity is 2. Because this is even, we know that it's tangent to the x-axis at that x value. What's another 0? Negative 2. Negative 2, its multiplicity is 3. So we know when, I can't spell, when x is 3, it's going to cross through. Okay, or it's passing, the graph will pass through. What's another 0? 1. If I have 1, what is the multiplicity? It's 1 that's odd as well, so it's going to cross the x-axis. And then finally I have 0, which also is odd, so it's going to cross the x-axis. So if we graph this, x minus 4 squared, x plus 2 cubed. So let's see. So if I do x minus 4 squared, x minus 2 cubed, right? And then I had x plus 2, x minus 1, and x minus 1. And this was a plus. I have a good time doing these videos all by myself with no one to watch or listen. So, let's look at this. This one's going to be a little tricky to see because at 4 it's going to do some weird stuff. But if I look at 4, do you see how it's coming down, it's grabbing the x-axis, and it's coming back up? It's tangent to. And then all my other zeros, right? So at this 1, at 0, it crosses through. and at -2 it crosses through. That's what we mean by multiplicity, and that's what I mean by the behavior of the function at those zeros. I hope that worked. It was a little bit of rambling today, but I hope it helped. I hope it made sense. If you have any questions, let me know.